Hi, y'all. There's a question about stability with regards to a particular homework problem, and so I thought I would just do a quick video covering some of those ideas. So let me, first of all, just from a general calculus overview standpoint, um, say you're given a function, and you probably we'll call it f of x for right now, just in standard math kind of stuff. But we'll discuss how to go further or give specific examples in a moment. So, so if you have a function and you're familiar with from your calculus treatments that if you take a derivative of this function, say f of x over dx, this graphically speaking gives you the slope. So the instantaneous slope at any location, slope at x. So whatever value I plug in for x, df of x dx will give me the instantaneous slope at that location. And so how this can be useful, for example, aside from just the slopes in general, is if we take df dx, if we take this and we set it equal to 0. Now you're probably already familiar. If you do this, when you set it equal to 0, what you generally end up doing is you set it equal to 0 and you find the values of x. And those values are generally referred to as the extreme values. Extreme values. I'll double underline that. You say, well, how does that work? Let's keep in mind if we have some function, and again, this is just some arbitrarily drawn function. Here's my x. Here's my function of x. If you just have some arbitrarily drawn function, something like that, yeah, it's still a function, okay. You notice that, okay, at any location where the slope is 0, right here, and again here, and here, there, down here, right there, and right there. At all of those values, they're called, those extreme values, a different way of saying it is it's a local max or min. In other words, it's where the graph goes from one slope, the slope changes. It goes from a positive slope to a negative slope, or it goes from a negative slope to a positive slope. Okay? So that's why we say it's a local minimum or maximum at any given point on the graph. So it looks like, as I've drawn this really ugly one, there's about, like you can see, about 6 places where you'll find a value of x. So if you do df dx equals 0, you'll get about 6 values for x where this statement is actually true. But there's a couple of extra pieces. So of course we're dealing with this generic function. We might not have it graphed out so that we can visually see it. But there's got to be a way for us to actually determine whether we're dealing with a minimum or a maximum. And that's the job of the second derivative. So we have to actually go one more step. So the second derivative, df x dx squared. Okay. And incidentally, I'll label this, x1. I'll label this one x2, x3, ... So I'll just let x1, x2, x3 represent the specific values where the extreme values are found. Okay, so x1 is the location of one of the extreme values, x2 is the second one, etc., etc. So if df of x dx gives us the slope, then the question is, what does d squared f of x dx squared give us? And in one sense, you could say, well, this just gives me the change in slope. Excuse me. Change in slope. which is, I guess, somewhat uninformative. What is interesting to know, however, is perhaps we don't need to know the specific change in the slope, but rather more generically, what we're interested in is taking the second derivative, f of x dx, x squared, evaluating at an extreme point, say x1, and seeing whether that the final answer is positive or if it's negative. We'll have to ask ourselves, what does that mean exactly if we're doing this, if we're seeing if it's positive or negative? Well, if the change in slope is positive, that means that my slope, let's say it starts out at some value, or graphically I'll just do it, say it starts out like this. If the change in the slope is positive, that means that, or positive at that location, that means it's going from a steeper incline to a less steep incline, for example. Right? That's if it's negative. Or if it's, this is a negative slope, you could do the same thing for a positive slope. Say it starts out like this and it's going to get steeper again. That's what it means for the slope, the change in the slope to be positive. Okay? So it's continually getting steeper. Or conversely, if it's negative, then it's continually getting less steep. Or, I don't know, you have these negative slopes in here as well, but you have some steep slope. And as you keep going, the slope itself is getting less and less steep as you go on in time. Okay? So if we think in terms of these slopes getting less steep or more steep, then we have an idea about what this finally gives us. So if we evaluate at an extreme value and get a positive number, that means that my slope is gradually leveling out, and then it'll go, right? So whatever my slope is, it's increasing. Conversely, if I have a negative value, then whatever my slope is, it's continually decreasing. And so you can see, okay, a negative value will be associated with a slope that decreases, and a positive value will be associated with a slope that's increasing. I usually tend to think about it like this. If I get a negative second derivative, it's a frowny face. And if I have a positive second derivatives, then it's a happy face. Okay? So we go through and we can see that, for example, x1, I guess I have it written here. The second derivative of the function evaluated at x1 is going to be negative. We're going to get this. So we can see that when we evaluate at x1, we're going to get a negative second derivative, and similarly for x3, x5, whereas x2, 4, and 6, those are going to give us those positive derivatives since they're sloping. What we say is we call this concave down, and this is concave up. You might also ask what happens if I evaluate the second derivative and set it equal to 0. Then you get the values of x that are called inflection points. It's where the slope transitions from being concave up to concave down, or vice versa. So, concave up, you get, I don't know why I'm doing this on the screen. You get these like S-type shapes, right? Concave up to, or concave down to concave up. Right here would be what's called an inflection point. Or concave up to concave down, again, an inflection point. Those aren't as important for the discussion, but just more general knowledge. Okay, so we have all of that. So then the other question, so we'll run some examples in a minute. But then the other question that we have is, what does it mean about stability? What does stability actually mean from a physics standpoint? And from a so the first thing that I would like you to envision is just envision a bowl for a second. So say you have a bowl. Okay, in fact, I'll dot it. Okay, there we go. Or you could think of it as being right side up. Okay, so a bowl. There we go. Now, there's something interesting about this. Of course, you could envision, for example, placing a marble at the top of this bowl, right here. And if you get it perfectly balanced, then everything's all fine and dandy. In fact, usually there's like competitions, for example, stacking golf balls or, balancing things. Generally, you think of balancing. Okay. Now, you know that this is actually stable, right? The ball, if you have it perfectly balanced on top of the bowl, or you stack the golf balls perfectly balanced, that's technically stable. Okay. But for example, say you flip over the bowl and you stick the marble in at the bottom, this would also be considered stable. So under both of these circumstances, it's considered stable. The question then becomes, what happens? What happens when, I'll use the word perturbed? Question mark. In other words, what happens if I come along and I give each of these little balls a little push? If I give it a little kick. Sorry, it's hard to see that. What happens then if I give them a little kick? Of course, in this case, the ball's just going to roll off the edge and you're done. Game, set, match. Whereas here, the ball's going to roll. It might roll upwards, but eventually it's going to start rolling back, and it'll roll back and forth. And assuming that there's some frictional force, eventually it'll settle back down to the bottom of the bowl. In other words, for this situation, if you perturb from equilibrium, you will no longer, or excuse me, if it's stable and you perturb it, it will no longer, it won't return to that stability. Okay. So what we call this is unstable. When something happens, it never returns back to the original state that it was in. Whereas here, we call this a stable. So it'll return back to its initial position. So unstable equilibrium. We call this a stable equilibrium. Okay. Okay. Well, hopefully you see now how the discussion about second derivatives will apply to the issue of stability. So here it is. So I'll say if given a function, a potential energy function, and I'll just do it like this. Okay, so I'm being more general in the sense of now I'm not thinking 1 dimensions, I'm thinking 3 dimensions. But if given a potential energy function, okay, we can find the force associated with that potential energy function. So the force of the potential energy function is just simply negative du dr. Okay. So we've done that just via the definition of work. So we have work is equal to the integral of f dot dr. And then we have, for conservative forces, that work is equal to the negative change in potential energy. Okay. So if we combine both of these together, you end up with something that says, hey, negative du dr is equal to f. Okay. Oh, excuse me. Maybe I shouldn't quite write it like that. Excuse me. Write like this. Okay, so we can get that. Now, of course, if we have a stability, or if we're in equilibrium, that tells us that our force must be equal to 0. Okay. In other words, this would be a case for equilibrium. And of course, if your force is equal to 0, your acceleration is equal to 0. So your object doesn't accelerate, so it's stable or in equilibrium. Okay, so number one is if we're given a potential energy function, we can find the equilibrium, where the locations where the object will be in equilibrium, namely the places where the derivative of the potential energy function is equal to 0. Okay. Or another way to say it is the extreme values. That's what we're really finding here. Okay. But now we want to be able to assess, are these locations where the object is in equilibrium, is it a stable equilibrium or an unstable equilibrium? And that's where we have to go to the inflection point, or the second derivative. So then the first derivative will tell us where the equilibriums are. The second derivative, in other words, dru squared equals 0. Oh, excuse me, it's not equal to 0. Taking the second derivative and evaluating at the extreme values will tell us if the equilibrium is stable or unstable. Okay. If this value is less than 0, it's stable. If it's greater than 0, it's unstable, right? Stability less than 0 means that you have a concave up potential energy, and so then if you perturb it, the force will return the ball back to the lowest position. It's a stable. Unstable, it's like having a ball on a bowl and pushing it off. Okay. So let's get some examples. Let's say we have a potential energy function, and I don't know. Okay, so let's go pretty general here. Let's say that we have a potential energy function, and I'll call it negative. Let's work in terms of variables. I'll call it alpha r to the n plus beta r to the m, where alpha, beta are constants. And we'll say that n and m are integers. Okay. I'm just kind of pulling something off the top of my head here. Now, if we want to know the force associated with this potential energy, we'd have to take a derivative, which is equal to negative du dr. So let's go ahead and do that. So a derivative of this would give us, we'll have a negative parenthesis alpha n r to the n minus 1 plus beta m r to the m minus 1. And we want, since we're interested in the extreme values, so finding extreme values, what we want to do is take this and set it equal to 0. So we'll say f of r is equal to 0. Okay, so 0 is equal to, we'll say alpha n r n minus 1 plus beta m r m minus 1. And notice I dropped the negative sign. I just multiplied through by negative 1. Well, if we want to find the values of, looking at this, we want to find the values of r. So, yeah, I guess we'll just work in terms of variables. Bm over alpha n, right? That's just some constant. I've got all those numbers. Equals, so this would be r to the n minus 1 divided by r to the m minus 1. Okay. Put that in parentheses. Oops, excuse me, I dropped a negative sign. You should yell at me. Right, I have a negative here, so there should be a negative there, which means there should be a negative here, which means this is positive. Whew, I was really worried there for a second. So I dropped a negative sign. Okay, well, you have, at the end of the day, this would be Bm divided by alpha n equals r n minus 1 minus m plus 1. Oh, goody goody. It's got some cancellation. And at the end of the day, you get beta m over alpha n. And I'll say to the 1 over n minus m equals r. So at least in this situation, where I have just some linear combination of two powers, apparently the extreme values are given by this expression. And I should note that if I'm not mistaken, I'd have to think about this for a second. I was going to say, it seems to me that there should be, I was going to say something about the number of extreme values that are actually available, but now that I think about it, no, maybe that's not okay. So in any case, there we go. And we're off and running like a bale of turtles. So now we have the location of the extreme values, and we would like to know whether those are stable or unstable. So we'll get rid of that. Let's go ahead and move this. So we have this. Here's our extreme values. And so the second one, the second derivative, oops, excuse me. So then we have u second derivative dr squared equals, well, okay, let's take this. So you get negative alpha n times n minus 1 r to the n minus 2 plus beta m minus 1 r to the m minus 2. So there's our expression, and we want to take this extreme value and substitute it in for r to the n minus 2 and r to the m. All right, that's essentially what we want to do. Well, I'll take that expression. Let's go ahead and I'll take this expression and let's simplify it just I think we can simplify it just a wee bit. Yes. Righto. So the idea being, and now I'm going to give a physics example, I'm going to assume that r is greater than 0. Okay. So r is the distance from the origin to the object. This value should always be greater than 0. And so what I'll get is I'll do this, du squared over dr squared equals negative alpha n minus 1 r to the n minus 2 over r to the m minus 2 times r to the m minus 2 plus beta m minus 1 r to the m minus 2. So I just multiplied by 1. And so you get something that says negative alpha n minus 1 times, well, I know what this is. This is just n minus m. So I'll get r to the n minus m plus beta m minus 1. And I just have r to the m minus 2. Whew! Well, I've got a value for this at least. That makes life a little easier. So I get equals negative alpha n minus 1. And I'll just substitute that in. This is beta m divided by alpha n plus beta m minus 1 r to the m minus 2. Righto. I guess here for the r to the m minus 2, I guess we could also substitute in a value there if we really wanted to. Right? This would just be beta m over alpha n to the m minus 2 divided by n minus m. Yeah, not very informative, but, you know, okay. So keep in mind, this is a positive value still. Let's take a look and see what happens when this term in brackets or parentheses is equal to 0. Okay. Kind of informative there. So we know that the inflection points, the inflection points are when the second derivative equals 0. Let's go ahead and find those inflection points, and then we'll have some idea about the relationship between n and m to determine, just looking at the equation, whether we have a negative or positive second derivative. So let's go ahead and set this equal to 0. And so we find out, assuming that this itself is not equal to 0, we have, go ahead and look at this. This will say that alpha n times n minus 1 times beta m over alpha n equals negative beta m times m minus 1. And we go, oh, goody, goody, look at this. Well, first of all, the nice thing is the bm cancels. B and m cancel right here. The plus sign, negative sign becomes a plus sign. And then the an here cancels the an there. And what are we left with? We are left with n, n minus 1 is equal to m minus 1, or n is equal to m. So under that condition, apparently, the extreme points end up also being the inflection points when n and m are the same value. Of course, you can play this whole rigmarole and say, well, what happens if I want this to be less than 0? Well, then I can put a less in sign and then a less sign. And so if n is less than m, then the second derivative ends up being less than 0. Cool. Okay. So we've got some idea about how to determine whether we have a concave up or concave down simply by comparing the two powers. I'll do arrows here. Simply by comparing the two powers in my equation. If n is less than m, and then notice n goes with the one that has the negative sign, then the potential at the extreme values will be a local minima. Cool. Okay. So let's go ahead and clear the table. So let's do this. So this takes us back to our homework problem now. Okay, so we've done all this background. And let's go ahead and take a look at the homework problem. So the homework problem, I have, at least I pulled one up, just random numbers, of course. But what I have is a potential energy function that is given by, let's see, well, okay, in terms of variables, I have a r to the negative 12th minus b r to the negative 6th. You say right away, oh, wait a minute, Greg. I can see here, here's the exponent for the negative term. And I can say that, wait a minute, remember up here when we were doing this, the condition was n must be less than m. That results in a second derivative evaluated at the extreme value, put RE, that will result in that being less than 0. In other words, being concave up. Now we note, though, that I have negative signs here. So you could say, well, wait a minute, okay, well, here's my condition, but if I multiply through by a negative sign, I have negative n. And if you remember about inequalities, when you multiply through by a negative sign, you have to flip the direction. Okay? So what I need is negative n to be larger than negative m. And then you see, okay, good. I have negative 6 is definitely larger than negative 12. So we're still good here. Okay, we're still dealing with a concave up, a local minima. Okay. Now for the specific problem I have, I'm given that the equilibrium distance, I'll put REQ, is equal to 1.13 times 10 to the negative 10th meters. Okay. And I'm given that the dissociation energy, so I'll just call this E dis. Given that the dissociation energy is 1.54 times 10 to the negative 18th joules. Okay. Ballparkish, this is roughly, if you're familiar with the units, this is roughly 10 eV. Just that's fairly standard. And the question asks you to find, okay, given these two values, the question asks you to find the values of A and B. So we're asked to, so we're given these, we're asked to find A and B. So we could do the same song and dance. We could say, well, du dr negative is equal to, okay, well, we have 12 times A r to the negative 13th, okay, minus B times 6. I guess I better put a negative sign here. I'll put negative 12. So we have minus B times 6 times r to the negative 7th. And that whole thing, inside there, we have a negative sign, an additional negative sign. And that is equal to our force. So we get something that says, okay, well, 12a r to the negative 13th minus b 6b r to the negative 7th. That's equal to my force, F of r. Setting my force equal to 0, you get 12a r to the negative 6th minus 6b. And we can do by nice magic, we have b divided by 2a. That's equal to our r to the negative 6th. Or, getting rid of the negative, we have 2a divided by b square rooted equals r, 6th rooted. So, you say this looks a little bit different because from the last expression, you notice how the alpha represented the term in front, or the term with the negative sign, and beta represented the term with the positive sign. So here it's same idea, it's just that everything has been flipped. So probably poor planning on my behalf, right? Here B represents the term with the negative sign, and A represents the term that's positive. So I apologize for that. I just thought I would let you know. Okay. Well, so now we have that r to the 6th is equal to 2a over b. And we have the dissociation energy, namely that this E dissociation, DIS, is equal to, say, negative u of infinity, right? How much energy does it take to actually take this thing to infinity? So negative u infinity minus let's see, U, R, E, Q. Okay, so we have that, putting that all together. So we have to sub and solve. Of course, the upshot is that U infinity, you notice if I make this infinity, I make this infinity, the potential energy becomes 0. So I get the disassociation energy is equal to the potential energy evaluated at REQ, which is pretty nice. So now I've got my two equations. I've got r to the 6th is equal to 2a over b, and I've already got my equation for the potential energy, so there's that. Let's go ahead and you know what's going to happen now. We just sub and solve. Well, golly gee whiz, Batman. I'll take this, I'll start with this. Let's say E, the disassociation energy, is equal to A divided by r to the 12th minus B divided by r to the 6th. Okay. I'm just trying to figure out some fancy-pantsy way of doing this. I guess what we'll do is we'll take r to the 6th times b divided by 2 is equal to a. We'll take this, and we'll go ahead and sub it in right here. So we get E is equal to, and we have b over 2 r to the 6th divided by r to the 12th minus b over r to the 6th. Well, that's nice. At least the r to the 6th cancels the r to the 12th, so that's a 6 now. So we get something that says the disassociation energy times r to the 6th equals b over 2 minus b. Or, if we'd prefer, negative 2 times the disassociation energy, r to the 6th is equal to b. There we go. Something bugs me slightly, but that's okay. Okay. So we have it. The thing that bugs me is I don't like the fact that this negative sign's here, so maybe I've done something goofy already. Figures. It's probably this negative sign here. Probably doesn't belong, which means that this is a negative. That's probably what it is, which means this is a negative and this is a positive. I get a negative and a positive. I get a negative and a positive. And so this ends up positive. That's definitely what it is. So I wasn't very careful there. There we go. Of course, now that we're given B, we can go back and find A. Namely, we can substitute in. And we get, that means that 2 times the disassociation energy times r to the 12th divided by 2 is equal to A. So now I've got my two results here. And of course, now it's just a matter of subbing in the numbers. But you can see already, since my r is 10 to the negative 10th, you can see that my b term is going to be something, 10 to the negative 60th times 10 to the negative 13th. So this is going to be like 10 to the negative 73rd. And this one's even worse, 10 to the 12th. Oops, get rid of those guys while we're at it. So it's going to be even smaller. Okay, so these numbers are really small. Okay, well, I think that's it for this discussion about stability. Actually, why don't I go ahead? I'll take a moment and queue up Excel, and I'll give you, I'll show you again how could you actually plot these to get an idea about what they look like. So give me just a second here. Okay, so we're back. Just for completeness, I thought, okay, let's run something where we actually plot these. So the problem actually asks you to plot them, and not that I actually expected you to plot them and somehow give the answer, but I just thought it would be a good exercise to start thinking about how to get these kind of things. Of course, there's more when it's Skinnachat, and I'm just going to do it on Excel here. Just because I know of the ubiquity of Excel availability, both on your computers, at your office, or or whatnot. But this is by far not the easiest way to do it. There's better programs out there. In fact, if you give me a moment, maybe I'll even review MATLAB, for example, just to give you a flavor of some other programs. So, but what we're going to do over here, I'm going to set some parameters. So things like A and B are always a good idea. And what I'll also do is I'll set a delta R step. So I'll put delta R here. Okay. And I better give an R naught. I can't use 0 because as you see from the potential energy function that we were dealing with, if I have R0, then the whole thing blows up and it doesn't work anymore. So for simplicity, just for scaling purposes at this point, I'm just going to put 1 and 1. And let's go ahead. Actually, I'll specify R naught. Okay, we'll call delta R. Yep. Actually, maybe I'll put range in here. Okay, and I'll put delta R. Okay. So let's start out R naught at just 1/10 of a meter. And let's say I want to plot it out for a full meter. So what I'll do is I'll do range divided by, say, 100. Oops. Oh, silly. Let's say I do B5 divided by 100. Okay, so I'll do 1/10 of a meter steps, or excuse me, 100th of a meter steps. Now there's a couple things that we need to do. I need to keep track of what R is, the distance. I would like to plot what the potential is. And of course, Microsoft thinks it knows what I want better than I do. No. Stop. Okay. Okay, it's the potential energy. Okay. And here's the F. Okay, the force. Like I said, Microsoft knows what it wants to do better than I do. So the first step is we're going to start this off with the initial. So this is the initials given by B4. So there we go. And now all we have to do is we have to actually calculate the potential energy function. Well, from the problem, I set that as $B $2. So the A value divided by the distance between the objects, that's given by D2. And I raised that to the 12th. Hokey fright. Okay. But wait, I'm not done. I also have to do my B value, which is B3. Excuse me, let me put the dollar signs in. B3 divided by, again, my radius, or my distance, D2. And this time it is to the 6th. Okay. So I have my A divided by the distance to the 12th minus my B value divided by the distance to the 6th. Well, bam. You see, hokey fright, this thing is big. It's big because my distance is pretty small. Okay. Well, my forces. Alrighty then. Well, this is, let's see, as we've specified, this is 12 times my A value, so $2, divided by my distance, D2, to the 13th. Yikes. Minus, okay, we have 6 times my B value, which is $B $3, 3, okay, divided by my distance, our D2, to the 7th. So let's see, 12, 13, okay, and then we have 6, and okay, I think we're good there. There we go. Cool. Well, let's go ahead. Now we're going to take D2, my previous cell value, and I'm going to add to it my delta R, which is given by $B $6. Boom. And now, if I'm not mistaken, the rest of this should be easy peasy. There we go. There we go. So again, making sure now it's using D3, yep, for the distances. And now we're just going to run the sucker. Let's do it like this. You can see, okay, these forces are rather large. We'll do it for 100. Nope, 100's not going to do it. Okay. Well, let's go for, I don't know. Let's go for 1,000 so long as the computer doesn't crash. You can see it's going slow. It's because I'm recording video at the same time. Okay, let's see what happens here. So if I plot these two suckers, is that far enough? 'Tis not. What? Okay. Oh, it's close. Okay, let's plot these two suckers, see what we get. Insert. Go scatter plot. That's rather disappointing, isn't it? Let's see what happens here. Let's make this 1. There we go. Good, 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 good. So it's just a scaling problem. So we see, and let's go ahead and we're going to scoot this down. Let's go ahead and make this 3. Okay. So we can really see, hey, if it dips down. Here's our minima. And we could actually click on it to figure it out. Okay. In fact, I'm pretty sure, let's go ahead and do one more thing here. Add. So there's that. We'll go ahead and put the forces in too. Ah, okay. Cool. Pretty awesome, eh? So now you can see actually both of them on the same, you can actually see them both on the same plot. Oh, let's take those data labels off. Don't need those. So we can see those on the same plot, which is always nice. Let us go ahead. There's one more thing that we should really know how to do here, and very helpful. Okay. So you notice I went into change chart type, and I'm going to go down here to combo. Okay. And what I want to do is, so this combo chart, what it allows you to do is actually plot 2 different things on the same plot with different axes. So you notice I'm still going to tell it to do a scatter plot, and I'm still going to tell it to do a scatter plot here. But do you notice that you have the secondary axis thing? And what I'll do is I'll go ahead and set the secondary axis. In other words, the left-hand side is going to be the axis for the potential energy function, and the right-hand side is going to be the axis for the force. Okay. So we'll go ahead and do that. So now you see here's the potential energy, here's the force, and we should probably put some axes titles on, just so that we know which one's which. So this would be the force in newtons. This would be potential energy in joules. Okay, there we go. Oh, excuse me. Should probably put that one in there. This is distance. Distance in meters. Boom. Pretty cool. So let's go ahead again. We're going to have to change the axes, of course, because I should have done that before I actually scaled everything. And here, let's go ahead and just make this 1. Make that easier to see. Same thing, we'll just make this 1. Make it easier to see. Boom. There you go. So you notice that right when the potential energy hits a minimum, the force is actually going to 0. And we could always, let's see, scale this a little bit better. Okay, so now you see maybe that's just too many. We don't have it out that far. Let's go like that. So this basically doubles the number of points, and you can see, okay, yeah, it's even closer. Pretty cool, huh? So we'll keep it there for right now, but if you ever have any questions on how to plot, of course, Python, MATLAB, these are programs that are actually optimized to do these kind of things, and so it would actually be better. You can get pretty much infinite precision so long as you're willing to wait long enough, and a better chart. In any case, I'll see you next time. Thank you for your attention.